What if the moments we call past and future are not as distant or separate as we believe, but exist simultaneously in ways we scarcely comprehend? This question has occupied thinkers, scientists, and observers for millennia, provoking reflection that spans civilizations, philosophies, and scientific revolutions. Time, in its most immediate sense, is the rhythm of change, yet defining it with certainty has proved elusive. Ancient cultures approached time not merely as a measure of change, but as a force intertwined with existence, cycles, and the cosmos. In the civilizations of Mesopotamia, time was intimately connected with the movement of celestial bodies. The Sumerians and Babylonians divided the day into units, observed lunar cycles, and created calendars to organize agriculture, festivals, and governance. To them, the past was inscribed in the regularity of the heavens, while the future unfolded according to the predictable patterns of celestial motion. In Egypt, time was often visualized through cycles of the sun, encapsulated in the journey of Ra across the sky. Religious and funerary texts, such as the pyramid texts, illustrated time as both linear in human affairs and cyclical in cosmic processes, intertwining mortality and eternity. Greek thinkers further formalized the conceptual understanding of time. Aristotle considered time a measure of change, dependent on motion and inseparable from events themselves. He described time as existing only insofar as there is change, asserting that without alteration, there would be no perception of temporal sequence. Yet, even within this framework, Aristotle recognized the complexity of understanding when an event occurs, highlighting the subtle interaction between continuity, succession, and human perception. Meanwhile, in Hellenistic and Roman philosophical thought, time was often associated with fate, determinism, and cosmological order, underscoring an implicit acknowledgement that what we perceive as past or future is embedded within a broader continuum. Religious texts in various traditions reflected similar contemplations. In Hindu cosmology, the cycles of yugas delineated ages of creation and dissolution, portraying time as a vast, repeating spiral. Buddhist philosophy addressed impermanence, emphasizing that all phenomena, including moments of experience, arise and pass. Yet, the perception of a distinct past and future is constructed by consciousness. Across these early frameworks, the notion of time was never solely linear. The past and future coexisted in rituals, predictions, and cycles, foreshadowing later scientific and philosophical debates about simultaneity and relativity. By the medieval period, Christian thinkers sought to reconcile temporal understanding with theological concepts. Augustine of Hippo, in his Confessions, grappled with the nature of the present, the weight of memory, and the anticipation of the future. He posited that the past exists only in memory, the asymptote, future only in expectation, and the present is fleeting, constantly vanishing into what is remembered or anticipated. Augustine's reflections were neither idle nor abstract. They constituted a rigorous attempt to map human experience onto the flow of time, acknowledging that perception and reality might diverge. In doing so, he laid the foundation for centuries of philosophical inquiry into whether time is a construct of human consciousness or a fundamental property of the universe. The scientific revolution introduced a radically different framework. Isaac Newton conceived of absolute time, flowing uniformly and independently of events or observers. In his Principia Mathematica, Newton defined time as a measurable continuum, moving at a constant rate regardless of motion, matter, or perception. This view facilitated precise measurement, prediction, and coordination in astronomy, navigation, and mechanics. Time became standardized through the invention and refinement of mechanical clocks, enabling societies to structure daily life, commerce, and governance according to an ostensibly objective temporal rhythm. Yet, even as these methods brought order, they also imposed a rigid framework that obscured the subtleties of temporal perception recognized by earlier thinkers. The 20th century disrupted this classical conception of time. Albert Einstein's theory of relativity revealed that time is not universal, but relative, intertwined with space in a four-dimensional continuum known as space-time. Clocks in motion, or subject to gravitational fields, measure time differently than stationary clocks in weaker gravitational conditions. The phenomena of time dilation, empirically confirmed in particle experiments and satellite technology, demonstrate that the intervals separating past, present, and future depend on the observer's frame of reference. Hermann Minkowski formalized this insight by presenting spacetime as a single, four-dimensional manifold in which all events, whether traditionally labeled past, present, or future, exist in relation to one another, challenging the intuition of a unique, flowing present. Contemporary physics continues to probe the nature of temporal reality. Quantum mechanics introduces phenomena that defy classical causal expectations, such as entanglement and superposition, in which particles appear to exist in multiple states or locations simultaneously. Certain interpretations, including the block universe model, suggest that all points in time coexist equally, implying that past, present, and future are not sequentially ordered, but are instead spatially arrayed within the space-time continuum. Experiments examining retrocausality explore the possibility that actions in the present may influence outcomes that conventional intuition regards as fixed in the past. Meanwhile, cosmological studies of the universe's expansion, the cosmic microwave background, and the origin of time itself from the Big Bang frame, temporal existence on a scale that dwarfs human comprehension, revealing the past and future as vast landscapes already encoded within the structure of the cosmos. Human perception of time adds another layer to understanding its apparent fluidity. While physics may describe time as a dimension within which events coexist, the human mind interprets sequences through memory and anticipation. Neuroscientific research reveals that the brain constructs the present by integrating sensory input with past experiences stored in memory and projections of expected future events. This synthesis forms the continuous narrative we call now, yet the so-called present is fleeting, often lasting only a fraction of a second before it is incorporated into memory. Experiments using temporal illusions demonstrate that perception can be shifted, with events appearing out of order or overlapping in ways that challenge linear intuition. In such contexts, the distinction between what has already occurred and what is yet to come becomes a matter of neural construction rather than objective division. Psychologists have long studied temporal cognition, investigating how humans experience duration, sequence, and simultaneity. Developmental studies show that infants gradually learn to differentiate past and future, suggesting that temporal understanding emerges through interaction with the environment. Cross-cultural research indicates that perception of time can vary widely. Some societies emphasize cyclical or event-based measures rather than linear clocks, blurring the sense of a strictly advancing present. Even in industrialized contexts, individual attention, emotional intensity, and physiological state influence the perceived passage of time. Moments of high stress or danger are remembered as elongated, while periods of routine may collapse into a seamless continuum, further reinforcing the notion that temporal experience is subjective, layered atop the underlying structure described by physics. Neuroscience identifies specific regions involved in temporal processing, including the cerebellum, basal ganglia, and prefrontal cortex. These areas integrate sensory input, internal rhythms, and memory to generate coherent temporal perception. Functional imaging demonstrates that temporal distortions occur under varying conditions, such as altered sensory feedback or shifts in attentional focus, revealing the malleability of the present. Studies of patients with neurological damage illustrate that disruptions in these networks can produce profound disorientation in perceiving sequences, underscoring that what we intuitively call past and future depends on the brain's capacity to organize events coherently. Within this framework, the illusion of a flowing present emerges as a sophisticated construction, overlaying a reality in which all events may already coexist in a space-time manifold. Cultural expression mirrors this complexity. Literature often manipulates temporal order to explore memory, causality, and the simultaneity of moments. In Marcel Proust's reflections on memory, past experiences resurface vividly, dissolving chronological distance. In music, compositions weave recurring motifs that resonate across temporal boundaries, suggesting that the emotional past is never wholly separate from the present listening experience. Similarly, visual art and ritual can embody layers of temporal reference, integrating ancestral events with contemporary observation. These human activities do not alter the physical structure of time, yet they demonstrate how subjective experience interlaces multiple temporal planes, giving the impression that past and future are continually present in perception. From these perspectives, the scientific and humanistic views converge. Physics presents time as a dimension in which events are arrayed, potentially existing simultaneously. Neuroscience shows that consciousness constructs the now by blending traces of the past with anticipations of the future. Culture reflects and amplifies this interplay, creating narratives in which chronological boundaries are permeable. Together, these strands suggest that the separation of past, present, and future is less an absolute truth than a feature of human cognition interacting with a universe governed by relativistic and quantum principles. The notion that the past and future might be happening now becomes less metaphorical and more a reflection of the intricate frameworks through which reality and perception intersect. Human perception of time adds another layer to understanding its apparent fluidity. While physics may describe time as a dimension within which events coexist, the human mind interprets sequences through memory and anticipation. Neuroscientific research reveals that the brain constructs the present by integrating sensory input with past experiences stored in memory and projections of expected future events. This synthesis forms the continuous narrative we call now, yet the so-called present is fleeting, often lasting only a fraction of a second before it is incorporated into memory. Experiments using temporal illusions demonstrate that perception can be shifted, with events appearing out of order or overlapping in ways that challenge linear intuition. In such contexts, the distinction between what has already occurred and what is yet to come becomes a matter of neural construction rather than objective division. Psychologists have long studied temporal cognition, investigating how humans experience duration, sequence, and simultaneity. Developmental studies show that infants gradually learn to differentiate past and future, suggesting that temporal understanding emerges through interaction with the environment. Cross-cultural research indicates that perception of time can vary widely. Some societies emphasize cyclical or event-based measures rather than linear clocks, blurring the sense of a strictly advancing present. Even in industrialized contexts, individual attention, emotional intensity, and physiological state influence the perceived passage of time. Moments of high stress or danger are remembered as elongated, while periods of routine may collapse into a seamless continuum, further reinforcing the notion that temporal experience is subjective, layered atop the underlying structure described by physics. Neuroscience identifies specific regions involved in temporal processing, including the cerebellum, basal ganglia, and prefrontal cortex. These areas integrate sensory input, internal rhythms, and memory to generate coherent temporal perception. Functional imaging demonstrates that temporal distortions occur under varying conditions, such as altered sensory feedback or shifts in attentional focus, revealing the malleability of the present. Studies of patients with neurological damage illustrate that disruptions in these networks can produce profound disorientation in perceiving sequences, underscoring that what we intuitively call past and future depends on the brain's capacity to organize events coherently. Within this framework, the illusion of a flowing present emerges as a sophisticated construction, overlaying a reality in which all events may already coexist in a space-time manifold. Cultural expression mirrors this complexity. Literature often manipulates temporal order to explore memory, causality, and the simultaneity of moments. In Marcel Proust's Reflections on Memory, past experiences resurface vividly, dissolving chronological distance. In music, compositions weave recurring motifs that resonate across temporal boundaries, suggesting that the emotional past is never wholly separate from the present listening experience. Similarly, visual art and ritual can embody layers of temporal reference, integrating ancestral events with contemporary observation. These human activities do not alter the physical structure of time, yet they demonstrate how subjective experience interlaces multiple temporal planes, giving the impression that past and future are continually present in perception. From these perspectives, the scientific and humanistic views converge. Physics presents time as a dimension in which events are arrayed, potentially existing simultaneously. Neuroscience shows that consciousness constructs the now by blending traces of the past with anticipations of the future. Culture reflects and amplifies this interplay, creating narratives in which chronological boundaries are permeable. Together, these strands suggest that the separation of past, present, and future is less an absolute truth than a feature of human cognition interacting with a universe governed by relativistic and quantum principles. The notion that the past and future might be happening now becomes less metaphorical and more a reflection of the intricate frameworks through which reality and perception intersect. The block universe hypothesis provides a framework in which all events, regardless of their conventional temporal labels, coexist in a four-dimensional space-time structure. Within this perspective, the distinctions we draw between past, present, and future are emergent features of consciousness navigating a pre-existing temporal manifold rather than intrinsic divisions of reality. Each event, from the earliest formation of galaxies to the smallest human decision, occupies a fixed position along the space-time continuum. Einstein's relativity underpins this model by demonstrating that simultaneity is relative. Two observers, moving differently, may disagree on the temporal ordering of events, yet both are correct within their frames of reference. Consequently, what one perceives as the past may appear concurrent with what another perceives as the present, emphasizing that temporal location is observer-dependent rather than absolute. Quantum mechanics complicates this picture further. Experiments in entanglement reveal correlations between particles separated across space and time in ways that defy classical causality. Certain interpretations suggest retrocausality, in which events in the present influence the apparent outcomes of measurements in the past. The famous delayed choice experiments, initially proposed by John Archibald Wheeler, demonstrate that decisions made after a photon passes through a double slit can retroactively determine whether it behaves as a wave or a particle. While these results do not imply literal time travel, they challenge the conventional linear narrative of cause and effect, illustrating that temporal order may be less rigid than everyday experience suggests. The implications of a universe in which past, present, and future coexist extend into philosophical questions about free will and determinism. If all events are already encoded in space-time, human actions might be understood as part of an immutable structure. Yet, this does not negate subjective experience. Conscious agents perceive choice and deliberation within the temporal framework of their cognition, while the broader structure of space-time accommodates these experiences without conflict. The interplay of determinism at the cosmic scale and emergent freedom in local perception exemplifies the subtle tension between physics and phenomenology, suggesting that time's illusion resides partly in the interface between observer and universe. Cosmological studies further illuminate the context in which all moments may exist simultaneously. Observations of the cosmic microwave background provide a snapshot of the universe as it existed approximately 380,000 years after the Big Bang, a relic frozen in time yet continuously accessible through observation. Light from distant galaxies reaches us after millions or billions of years. Yet when astronomers interpret it, they are effectively viewing the past as present data. This reinforces the notion that temporal boundaries are not fixed but relational. Observing Earth's quasar 10 billion light-years away is akin to encountering its ancient light in the present. The universe, in effect, allows direct interaction with past events without violating physical law, emphasizing that time can be approached as a landscape rather than a strict sequence. Technological applications provide tangible demonstrations of temporal relativity. Global positioning system satellites account for time dilation resulting from both velocity and gravitational differences, ensuring that positional data remains accurate. Without such corrections, discrepancies of several microseconds per day would accumulate, producing navigational errors. These practical examples illustrate that even in routine life, the malleability of temporal measurement is real and significant, embedding relativistic time into the infrastructure of contemporary society. Our daily experience, however, seldom confronts these subtleties, leaving intuition bound to a seemingly universal flow that physics consistently undermines. The intersection of neuroscience, physics, and philosophy highlights an essential tension. While the universe may encode all moments, human consciousness necessarily experiences them sequentially. Memory, expectation, and attention create a sense of continuity, a narrative thread binding disparate events into a coherent story. Yet research on temporal illusions, such as the chronostasis effect in eye movements or the subjective stretching of moments in high adrenaline situations, underscores that the now is a construct that overlays a broader temporal reality. In this context, both past and future can be said to exist simultaneously, with perception selectively highlighting segments of a pre-existing temporal landscape. Cultural reflections continue to mirror these insights. In ritual practices across civilizations, participants symbolically bridge past and future, enacting traditions that render ancestors present and projecting intentions forward to descendants. In music, recurring motifs evoke memory while anticipating harmonic resolution, creating simultaneous engagement with past and future within the temporal flow of listening. Literature often collapses narrative time, interweaving flashbacks and foreshadowing, illustrating that human representation of time, like the physical universe itself, resists strict linearity. These artistic and ritualistic manifestations reinforce the notion that temporal experience is multidimensional, simultaneously containing multiple moments in consciousness. Within both science and human experience, then, the past and future are not strictly separate from the present. They exist as embedded dimensions, accessible through observation, memory, projection, and cognition. Physics provides a structural framework in which this coexistence is manifest, while neuroscience and psychology explain the subjective filtering that creates the appearance of temporal flow. Culture and art provide further evidence that humanity has long intuited this simultaneity, encoding it symbolically and experientially. Collectively, these perspectives suggest that time, rather than being a simple river carrying events from past to future, is a complex tapestry in which all events are interwoven, each present moment threaded through an expansive temporal continuum. The human mind navigates time not as a passive observer, but as an active constructor, continuously synthesizing sensory input, memory traces, and anticipatory models to create a coherent present. Memory itself is not a static archive. It is reconstructive, drawing upon past experiences to inform current perception. Neuroscientific studies indicate that recalling an event engages many of the same neural circuits as experiencing it, effectively bringing past moments into a form of immediate presence. Simultaneously, the brain generates predictive models, anticipating what is likely to occur in the next moments. This dual process, reconstructing memory while forecasting the future, renders the present a nexus in which past and future converge, suggesting that the boundaries separating temporal categories are porous at the level of conscious experience. Attention further modulates temporal perception. The mind does not process all sensory information uniformly. It prioritizes certain stimuli, selectively highlighting aspects of the environment while backgrounding others. Temporal distortions often accompany shifts in attentional focus, as demonstrated in experiments where repeated visual or auditory stimuli appear compressed or expanded in duration depending on cognitive load. These phenomena illustrate that even when external events unfold according to uniform physical laws, subjective time is malleable. The experienced now becomes a filtered representation, blending past sensory input and future anticipatory constructs, providing a continuous but intricately constructed temporal tapestry. Emotion profoundly influences this construction. Events of high salience, whether frightening, joyous, or novel, are remembered with greater intensity and perceived as temporally elongated. Conversely, mundane or repetitive experiences can collapse into a seamless flow, making the passage of time seem faster than the objective measurement would suggest. Neurochemical mechanisms, including the release of norepinephrine and dopamine, modulate the encoding of temporal information, linking the subjective experience of time with physiological processes. In this way, human perception of time is not merely a passive reflection of physical sequences, but a complex interaction among cognition, emotion, and environmental input, further reinforcing the notion that past and future are accessible within the present experiential frame. Language and conceptual thought also shape temporal understanding. Most cultures employ grammatical structures that distinguish past, present, and future. Yet, these linguistic divisions do not always correspond to absolute reality. Some languages encode time in ways that emphasize spatial orientation or cyclical patterns rather than linear sequencing, subtly altering the perception of simultaneity. The habitual use of temporal markers in speech and thought reinforces cognitive patterns that differentiate moments. But the underlying neurological and physical substrate remains capable of integrating events across traditional temporal boundaries. Such observations suggest that the conventional segmentation of time is partly a cognitive artifact, layered over a reality in which multiple temporal states coexist. Memory consolidation and retrieval illustrate the constructive interplay between temporal layers. The hippocampus plays a central role in encoding experiences, yet recall engages a dynamic network, including the prefrontal cortex, parietal regions, and sensory cortices. Each act of remembering involves reconstruction influenced by current context, expectations, and attentional state. From a physical perspective, the information associated with past events remains embedded in neural circuits, much as light from distant stars remains accessible across cosmic distances. In both cases, accessing information effectively collapses temporal separation. The past is present in the neural or observational data, ready to be engaged and interpreted in the now. Studies of altered temporal perception provide further insight. Individuals experiencing dissociative states, meditative absorption, or extreme sensory deprivation report a blurring of past and future, describing a sense in which all moments coexist within a singular present. Neurological evidence supports these reports. Activity patterns in default mode networks, which integrate memory, self-referential thought, and anticipation, become highly synchronized, producing a subjective perception of temporal unity. These experiences, while extreme, suggest that under ordinary conditions, consciousness continuously mediates the simultaneous presence of past and future, albeit filtered by attention, memory fidelity, and predictive modeling. Technological augmentation has begun to illuminate and manipulate temporal perception externally. High-speed imaging, virtual reality, and neural interface experiments allow humans to experience phenomena at different temporal scales, compressing or expanding the apparent flow of events. In these contexts, the interplay of perception and physics becomes evident. While the external world continues along its measured timeline, conscious experience can interact with past and future representations in ways that defy linear intuition. This convergence between observation, neural processing, and technology underscores a central theme. The past and future, while physically embedded in space-time, are accessed and modulated continuously in the present, demonstrating the profound entanglement of cognition with temporal reality. Cultural practices, once again, reflect and amplify these insights. Rituals commemorating ancestors, storytelling traditions, and ceremonial reenactments bring the past into immediate presence. Similarly, planning, anticipation, and goal setting orient participants toward future possibilities, blending foresight with present action. In art, music, and literature, motifs often evoke multiple temporal layers, creating experiences in which historical events, present reflection, and future expectation are simultaneously apprehended. Collectively, these practices illustrate that humans have long recognized and exploited the inherent simultaneity of temporal dimensions, reinforcing what physics and neuroscience now articulate. That time's apparent linearity is a product of perception, not a fundamental property of the universe. The measurement of time has long been intertwined with humanity's quest to understand its structure. In ancient civilizations, sundials, water clocks, and later mechanical clocks allowed precise division of hours and minutes. But these instruments only marked apparent temporal flow, rather than capturing the deeper complexity revealed by modern physics. The refinement of astronomical observation, beginning with Babylonian records of lunar cycles and continuing through Ptolemaic ephemerides, allowed prediction of celestial events, reinforcing a conception of temporal regularity. Even so, these measurements reflected patterns, not the intrinsic nature of time. They tracked change without interrogating the simultaneous existence of past, present, and future events that later scientific insights would suggest. In the 17th century, the invention of pendulum clocks by Christian Huygens and further refinements by John Harrison for marine chronometers enabled unprecedented precision, essential for navigation and coordination. The ability to standardize temporal intervals imposed a linear framework on human activity, fostering industrialization and global synchronization. Yet physics was preparing to overturn this intuitive linearity. While clocks measured intervals uniformly on Earth, Einstein's relativity demonstrated that identical clocks in motion relative to one another or subject to different gravitational fields would record differing durations. Such experiments, later verified with atomic clocks on fast-moving jets or orbiting satellites, revealed that temporal intervals are not absolute but contingent, highlighting a disconnect between human-engineered precision and the underlying structure of space-time. In contemporary physics, the concept of simultaneity is further challenged. Events separated by vast distances may appear sequential to one observer, while simultaneous to another, depending on their motion and reference frame. The Lorentz transformations mathematically formalize this principle, showing that time coordinates are relative, interwoven with spatial coordinates into a unified fabric. This realization forms the backbone of the block universe model, in which all events, regardless of conventional temporal labels, exist within a four-dimensional continuum. Observers experience only slices of this continuum as now, yet all slices coexist, accessible in principle to any sufficiently informed frame of reference. In this framework, the past and future are ever-present dimensions, integrated within the cosmic structure. Psychological case studies provide complementary insight. Longitudinal observations of individuals recovering from neurological trauma reveal that memory and anticipation are malleable, highlighting the brain's role in temporal construction. For instance, patients with hippocampal damage may experience an impaired ability to recall past events or simulate future scenarios, demonstrating that temporal perception is contingent on neural architecture. Conversely, experiments with healthy individuals using virtual reality environments show that manipulating sensory input can compress or expand subjective duration, reinforcing the idea that the present is a cognitive synthesis of multiple temporal layers. These findings illustrate the parallel between neural networks encoding temporal information and the physical universe encoding events within space-time, emphasizing that past and future are continually accessed within the present moment. At the cosmic scale, the light from distant stars and galaxies serves as a natural archive, carrying information from billions of years in the past into the observer's present. Astronomers reconstruct stellar evolution by interpreting this incoming light, effectively bringing the past into immediate perceptual relevance. Gravitational lensing and time delay measurements provide additional methods to observe historical events as present phenomena. From the vantage of the human observer, cosmic events that unfolded eons ago are no longer abstract. They exist tangibly within the immediate perception, illustrating a concrete instance in which the past is not merely remembered but directly observed. Similarly, predictive models in astrophysics allow scientists to anticipate future configurations of galaxies, planetary orbits, and cosmic background radiation, integrating foresight with current observation. The universe, in this sense, embodies the simultaneity of temporal dimensions, both in physical reality and in human comprehension. In daily life, technology subtly enacts similar principles. Real-time data feeds, predictive algorithms, and global networks compress temporal experience, making distant events immediately accessible and allowing actions to influence outcomes that would traditionally be considered temporally distant. Economic markets, weather modeling, and digital communication exemplify a convergence of perception, data, and predictive calculation, demonstrating that past information and future projections are effectively present in decision-making. These examples highlight the interplay between objective temporal events encoded in physical law and their interpretation, manipulation, and integration in human cognition, further blurring conventional distinctions between past, present, and future. The confluence of physics, neuroscience, and cultural practice underscores an essential insight. The apparent linearity of time is an emergent phenomenon arising from perception, memory, and attention, rather than an absolute structural property of the universe. While everyday experience reinforces a sequential ordering of events, careful observation and measurement reveal a more intricate reality, one in which past and future coexist as tangible dimensions, accessible through observation, cognition, and interpretation. The illusion of flowing time, so persistent in ordinary consciousness, may therefore be understood as a functional construct necessary for navigating a complex world, yet not reflective of the universe's total structure. Experiments in relativity offer compelling demonstrations of temporal malleability. In 1971, the Hafele-Keating experiment flew atomic clocks on commercial airliners around the world, comparing elapsed time with synchronized reference clocks on the ground. The results confirmed predictions of special and general relativity. Clocks on planes, traveling at high speeds and at varying altitudes, experienced measurable differences in elapsed time compared to stationary clocks. The experiment concretely illustrated that temporal intervals are observer-dependent, providing empirical evidence that time is not universally uniform, but is intimately connected to motion and gravitational context. Such findings underscore that what one observer experiences as the present may differ from another observer's now, making the conventional distinction between past and future relative rather than absolute. Quantum phenomena introduce further complexities. Consider the phenomenon of entanglement, in which two particles separated by vast distances exhibit instantaneous correlations in their properties. Measurements on one particle appear to affect the other, regardless of separation, challenging classical notions of causality and linear temporal flow. Experimental setups, such as Bell test experiments, have repeatedly confirmed these correlations, suggesting that certain aspects of physical reality are non-local and that conventional sequentiality is insufficient to fully describe quantum interactions, while not implying that macroscopic events literally transcend time. Entanglement demonstrates that at fundamental levels, the universe encodes relationships that do not conform to classical temporal ordering, implying that the framework of past, present, and future is more fluid than intuition might suggest. Delayed choice quantum experiments expand upon this notion. In these experiments, a photon passes through a double-slit apparatus, and the choice of whether to measure its wave-like or particle-like behavior is made after the photon has traversed the apparatus. Results consistently show that the choice of measurement appears to retroactively determine the photon's behavior, challenging straightforward causal narratives. Physicists interpret this as evidence that events at the quantum level are not fixed until observed, intertwining temporal dimensions in ways that allow present decisions to influence the manifestation of past phenomena. The implications resonate with philosophical reflections. If observation and measurement integrate past and present within a unified framework, then the linear conception of time becomes an emergent property of macroscopic averaging, not a fundamental feature of reality. On the human scale, perception experiments echo these physical principles. Studies using temporal order judgment tasks demonstrate that the brain can misattribute the sequence of rapidly presented stimuli, sometimes perceiving later events as occurring before earlier ones. Similarly, experiments with temporal binding reveal that actions and their consequences are neurologically fused, compressing the perceived interval between cause and effect. Such results indicate that the mind does not passively receive temporal information, but actively constructs temporal sequences, blending past, sensory input, and anticipated outcomes into a coherent narrative. In effect, consciousness accesses multiple temporal layers simultaneously, with the present emerging as a constructed focal point rather than an absolute boundary. memory and anticipation further illustrate this simultaneity. The act of remembering an event involves reactivation of neural patterns that encode sensory, emotional, and contextual information, effectively bringing a past moment into the experiential present. Anticipating the future engages overlapping networks, projecting potential sequences of events that guide action. Functional MRI studies show that similar regions are involved in both memory retrieval and future simulation, highlighting that the brain does not strictly separate temporal dimensions, but integrates them into a continuous experiential field. The interplay of these cognitive processes creates the subjective sense of flow. Yet, underlying this flow is a complex architecture in which past and future are continuously accessible within the immediate present. Technological observation reinforces these insights. High-frequency financial markets, for example, operate on temporal scales that approach microseconds, requiring traders and algorithms to respond to past data, present conditions, and predictive models of future behavior in real time. In virtual environments, augmented reality and simulation experiments allow individuals to manipulate time perception, experiencing events in compressed or expanded temporal sequences. These systems demonstrate that operationally, past and future are constantly engaged in the present, whether in neural processing, technological response, or conscious awareness, further blurring the intuitive boundaries of temporal flow. Astronomical observation continues to exemplify this simultaneity. Light from distant supernovae, traversing billions of light years, carries historical information into the present observational frame. Gravitational lensing can produce multiple images of the same event, arriving at staggered times, yet representing a single physical occurrence. Similarly, predictive modeling in astrophysics allows scientists to anticipate celestial configurations far into the future, integrating these projections with present data. In both cases, the human observer perceives and interacts with events traditionally labeled past or future, illustrating that temporal categories are not rigid constraints, but aspects of a broader, continuous temporal landscape. Collectively, these examples from physics, psychology, neuroscience, and astronomy converge on a consistent insight. The past and future are not distant abstractions, but dimensions embedded within the present. Observation, cognition, and technological mediation allow simultaneous engagement with these dimensions, rendering the conventional flow of time a functional illusion rather than an intrinsic property. Conscious experience navigates this structure, highlighting slices of the continuum as immediate, while continuously accessing layers that would otherwise be classified as past or future. In this light, the universe is a tapestry of moments, each woven with threads of preceding and succeeding events, all present within the structure of space-time itself. Throughout human history, contemplative practices have provided direct insight into the experience of temporal simultaneity. In Buddhist meditation, practitioners cultivate mindfulness of each moment, observing the arising and passing of thoughts, sensations, and emotions. This close attention to experience reveals that the present is not a static point, but a dynamic interface between memory and anticipation. Advanced practitioners report a diminished sense of linear time, perceiving past experiences as accessible within immediate awareness and future possibilities as vividly present in the mind's eye. Neuroscientific studies corroborate these reports, showing altered activity patterns in the prefrontal cortex and default mode network, regions implicated in temporal integration, self-referential thought, and memory retrieval. In other contemplative traditions, similar phenomena emerge. Yogic practices in India emphasize awareness of breath and bodily sensations as anchors in the present. Yet extended practice can lead to a perception in which discrete moments of the past and future are experienced within the ongoing now. Sufi meditation and other mystical practices also explore temporal fluidity through repetitive chanting, movement, and focused attention, creating a heightened sense of immediacy while simultaneously accessing memories and anticipations. Across these cultures, the subjective experience of time aligns with the scientific notion that temporal dimensions coexist, accessed by the mind in ways that challenge conventional sequencing. Anthropological observations reveal that many traditional societies perceive time less linearly than industrialized cultures. Event-based, cyclical, or relational frameworks dominate, prioritizing social and ecological context over sequential chronology. In these systems, storytelling, ritual, and seasonal cycles integrate past events into the lived present and project future expectations, often treating them as actively present influences on communal life. Ceremonial reenactments, such as harvest festivals or ancestor commemorations, function as tangible bridges, bringing historical experience into immediate awareness and guiding contemporary decisions with foresight. Time, in these contexts, is an ongoing continuum in which past and future are woven into everyday existence rather than separated into discrete compartments. Artistic expression consistently mirrors this simultaneity. In music, the repetition of motifs, themes, and harmonic sequences invokes memory while anticipating resolution, allowing listeners to experience multiple temporal layers simultaneously. Visual arts, from historical frescoes to modern installations, often depict narratives across time, juxtaposing events traditionally separated into past, present, and future. Literature frequently collapses chronological order, interweaving flashbacks, foreshadowing, and non-linear narrative techniques, creating a reading experience in which the past informs the present and the future emerges within the narrative flow. In all these domains, humans intuitively construct experiences in which temporal categories coexist, aligning perception with the physical and cognitive realities of time. Experiments in psychology illustrate that temporal perception can be shifted intentionally or incidentally. Mindfulness training and meditation exercises increase awareness of the transient nature of the present while enhancing the accessibility of memory and anticipation. Neuroimaging studies reveal increased connectivity between hippocampal and prefrontal regions, suggesting that the mind simultaneously encodes and retrieves temporal information during focused awareness. Sensory deprivation or controlled environmental stimuli similarly produce temporal distortions, with participants reporting the blending of past and future into a seamless present. These findings underscore that temporal experience is actively constructed and malleable, with attention, intention, and context determining the degree to which past and future are perceptually integrated. Even in daily life, subtle examples emerge. Reading historical accounts allows individuals to perceive events separated by centuries as immediately present within the mind's comprehension. Planning for future obligations engages overlapping cognitive networks, linking anticipated outcomes with present decisions. In technology-mediated environments, real-time data visualization and predictive analytics compress temporal distances, allowing present actions to interact with past data and projected trends. Across these domains, the human experience of time is continually negotiating between linear sequence and simultaneous access, demonstrating that temporal boundaries are flexible and context dependent. Philosophical traditions have long recognized this complexity. Henri Bergson distinguished between measurable, clock-based time and lived, experiential duration, emphasizing the fluidity and indivisibility of conscious experience. Immanuel Kant proposed that time is a framework imposed by the mind to organize sensory input, not an intrinsic property of reality. Contemporary thinkers extend these insights, noting that the brain's predictive and reconstructive capacities integrate multiple temporal layers into coherent experience, aligning phenomenology with relativistic and quantum models of the universe. In this sense, philosophy, psychology, and physics converge on the insight that what is conventionally called past and future is continuously present within perception and cognition. Observations in cosmology provide vivid examples of time's expansive and layered structure. Light from galaxies billions of light years away reaches Earth after traversing immense stretches of space, allowing astronomers to witness events that occurred in the distant past as though they were present. Supernovae, pulsars, and quasars reveal information about matter and energy at epochs far removed from contemporary experience. Yet, these ancient signals are immediately observable, collapsing temporal distance into perceptual immediacy. Gravitational lensing can create multiple images of the same cosmic event, appearing at different times from the observer's perspective, while originating from a single occurrence, further illustrating that chronological labeling is contingent upon observational context rather than intrinsic property. On a more human scale, relativistic effects subtly influence our perception of temporal flow. Satellites in orbit experience both velocity-based and gravitational time dilation relative to observers on Earth. GPS systems must account for these discrepancies to maintain precise positional information. While the differences are minuscule in daily experience, they demonstrate that time is not uniform even across familiar scales. Human consciousness, unaware of these minute variations, perceives a continuous flow, highlighting the distinction between physical temporal structure and phenomenological experience. In effect, the universe operates according to principles that allow past and future to coexist within a flexible, observer-dependent framework, even if the human mind only apprehends a linear approximation. Experimental psychology provides complementary insights. Studies on interval timing reveal that humans do not experience time uniformly. Durations of identical physical length can be perceived differently depending on attention, emotional state, and context. The stopped clock illusion, for example, demonstrates that brief temporal intervals can feel elongated, revealing that the subjective present is actively constructed. Similarly, temporal binding in action perception studies shows that consequences of an action are perceived as closer to the initiating event than they physically occur, blending past and present within experience. Such findings reinforce the notion that consciousness continuously mediates between multiple temporal layers, integrating past memories and future anticipations into the ongoing now. Neuroscience illustrates that memory, attention, and prediction are inseparable components of temporal construction. The hippocampus encodes spatial and temporal sequences, forming a scaffold upon which episodic memory and future simulation are constructed. Functional imaging reveals that imagining future events recruits overlapping neural circuits with remembering past events, emphasizing the brain's integrative approach to temporal information. Even when observing real-time events, cognitive processing interleaves sensory input with memory and predictive modeling, producing a conscious experience in which multiple temporal dimensions coexist seamlessly. This dynamic interplay underscores that the present moment is an emergent phenomenon arising from the continuous engagement with past and future. In the realm of culture, architectural and ceremonial designs encode temporal layering. Stone circles, astronomical observatories, and ritual sites often align with solar, lunar, or stellar cycles, embedding past observations and future expectations into a spatial temporal framework. Festivals and seasonal rituals commemorate historical events while guiding anticipatory action, creating a living continuum in which human activity connects multiple temporal planes. Art, literature, and music continue to leverage repetition, foreshadowing, and flashback techniques to evoke experiences that simultaneously engage memory and anticipation, offering a sensory representation of temporal simultaneity. Technological environments extend these capacities. Data streams, predictive modeling, and simulation allow humans to interact with historical information, current conditions, and projected scenarios in real time. Economic forecasting, weather prediction, and digital communication rely on integrating past and present data to anticipate future outcomes, effectively bringing multiple temporal layers into the operational present. These systems, while constructed, demonstrate the practical reality of simultaneity. Past data informs present action, which shapes anticipated outcomes, weaving temporal dimensions together in a continuous operational fabric. Even everyday experiences illustrate this principle. Observing distant landmarks, reading historical texts, planning for future appointments, or listening to music can all create a sense in which past and future exist alongside the present. Neuroscientific studies confirm that during these activities, brain networks integrate information across temporal scales, allowing cognition to access and manipulate representations of events removed from chronological immediacy. In this sense, consciousness constantly navigates a layered temporal landscape, selectively highlighting sequences as present while maintaining access to the surrounding temporal context. Historical measurement systems provide further insight into temporal perception and simultaneity. Ancient civilizations used water clocks, sundials, and astronomical observations to structure daily life and ritual. Yet these devices tracked cyclical patterns rather than defining a strict linear sequence. Mechanical clocks later imposed a uniform measure, but even with increasing precision, time remained relative. Galileo observed that pendulum periods are consistent under uniform conditions, yet any alteration in gravity or motion affects duration. Modern atomic clocks reveal even more subtle variations, especially under relativistic conditions, demonstrating that temporal measurement is influenced by position, velocity, and gravitational context, further illustrating that past and future exist continuously relative to each observer's frame. Experimental studies in perception complement these historical insights. Subjects engaged in rapid sequences of visual or auditory stimuli often misreport the order of events, demonstrating that temporal perception can be altered by cognitive processing. Tasks involving prediction and response show that anticipatory modeling effectively brings future information into immediate awareness, while recall and recognition integrate past experiences. Together, these studies underscore that human cognition continually constructs the present by blending past and future information, creating a seamless temporal field within which events are accessible beyond strict chronological separation. Quantum experiments provide striking examples of temporal simultaneity at the microscopic level. In entanglement studies, particles separated by vast distances exhibit correlations in real time, regardless of the interval between measurement events. The observed outcomes demonstrate that the state of one particle is linked instantaneously to its partner, suggesting that conventional sequential causality does not fully describe these interactions. These results, repeatedly confirmed in laboratory conditions, reveal that quantum systems encode relationships across spatial and temporal separation, challenging the notion that past and future are fixed or sequential, and indicating that multiple temporal states can be simultaneously manifest within a single experimental framework. Delayed choice experiments further highlight the fluidity of temporal order. When the photon passes through a double-slit apparatus, the choice of measurement applied after its transit influences the manifestation of its prior behavior, whether wave-like or particle-like. This apparent retroactive determination does not violate physical laws, but underscores the capacity of quantum phenomena to integrate past and future conditions into the present observational outcome. Similar experiments with entangled particles reinforce the principle that quantum-level events are not strictly temporally localized, allowing correlations and probabilities to extend across what we conventionally define as past, present, and future. Brain imaging studies reveal corresponding patterns in human cognition. Functional MRI scans indicate that episodic memory retrieval and future planning engage overlapping networks in the hippocampus, prefrontal cortex, and parietal regions. Neural activation during recollection of past events often mirrors activity during anticipation or simulation of future scenarios, reflecting an integrative mechanism in which temporal information is continuously processed and interwoven. Even while observing present stimuli, the brain accesses stored experiences and predictive models simultaneously, creating a continuous, layered temporal perception in which past and future coexist within conscious experience. Cultural practices illustrate the integration of temporal dimensions in daily life. Ritual reenactments, festivals, and commemorative ceremonies often bring historical events into immediate presence, guiding social behavior and reinforcing collective memory. Seasonal observances and cyclical calendars encode knowledge of past environmental patterns while preparing communities for future conditions, embedding anticipatory action within present awareness. Oral storytelling traditions maintain historical continuity, blending memory, interpretation, and expectation into narratives that function across multiple temporal layers, allowing listeners to perceive the past as alive in the present and to anticipate future developments through cultural scripts. Daily human experience continually accesses temporal simultaneity. Listening to music, following a narrative, or engaging in skilled action requires integrating past patterns, present sensory input, and expected outcomes. Athletes, musicians, and drivers predict immediate consequences while drawing upon prior experience, effectively collapsing temporal distance in real time. Cognitive studies demonstrate that when people perform rapid sequential tasks, the brain anticipates future states and reconstructs prior steps simultaneously, producing a perception in which multiple temporal frames are actively present within the ongoing moment. Technological environments extend these capacities on a broader scale. Real-time monitoring systems, predictive algorithms, and simulation platforms allow human operators to integrate historical data, current observations, and future projections in decision-making processes. Examples include weather prediction, traffic management, stock market analysis, and digital communication networks, all of which rely on simultaneously accessing multiple temporal layers. These practical applications reveal that operationally, past, present, and future are continuously interwoven, not only in conscious perception, but in engineered systems that enhance temporal integration in human activity. Neuroscientific research continues to uncover mechanisms supporting these experiences. Studies on temporal binding show that actions and consequences are neurologically fused, compressing perceived intervals between cause and effect. Experiments with temporal order judgment illustrate that rapid sequences of events can be perceived in altered order, revealing that the brain constructs temporal sequence rather than passively registering it. Attention, memory, and predictive modeling are central to this construction, producing a present experience in which past experiences and anticipated outcomes coexist within a unified cognitive field. Astronomical observation reinforces these insights. Observing light from distant supernovae, quasars, and other celestial phenomena allows scientists to perceive events that unfolded billions of years ago in the present. Predictive modeling of stellar evolution and orbital dynamics enables anticipation of future configurations, which can then be tested against observations. These processes demonstrate that temporal information from past and future events is effectively present in both human perception and scientific measurement, exemplifying a universe in which multiple temporal states coexist within operational and observational frameworks. Human perception experiments reveal the subtle ways temporal simultaneity manifests in everyday cognition. Studies on rapid visual sequences show that when stimuli are presented in quick succession, participants often misjudge the order of events, perceiving later occurrences as happening before earlier ones. This demonstrates that temporal experience is actively constructed by neural processes rather than passively recorded. Similarly, auditory experiments reveal that listeners integrate overlapping sounds across brief intervals, creating a coherent perception that blends past notes with anticipated continuations. These findings illustrate that the mind continuously merges past sensory input with predictions of the immediate future, producing a seamless present. Neuroscientific research adds further precision to these observations. Functional MRI and electroencephalography studies reveal that when individuals engage in tasks requiring memory recall or anticipation, overlapping networks in the hippocampus, prefrontal cortex, and parietal lobes become active. These regions encode spatial and temporal relationships, allowing the brain to integrate past experiences with potential outcomes. Even in real-time sensory processing, the brain simultaneously references stored experiences and predictive models, constructing a present in which multiple temporal layers coexist. Attention and working memory modulate the prominence of these layers, emphasizing some sequences while backgrounding others, resulting in the subjective sensation of a continuous, dynamic now. Cultural rituals and practices provide tangible examples of temporal layering. In many societies, festivals commemorate past events while directing community attention towards seasonal or societal cycles, effectively situating participants within an active continuum of time. Ancestor veneration, ceremonial reenactments, and oral storytelling maintain historical memory while shaping present behavior and future expectations. Agricultural cycles, such as planting and harvesting traditions, incorporate accumulated knowledge of past conditions to guide present action, ensuring survival while anticipating future environmental changes. Across these practices, the past and future are not abstract. They are continuously present within the structure of social and ecological life. In artistic expression, temporal simultaneity is often intentionally evoked. Musical compositions rely on thematic development, repetition, and harmonic progression, allowing listeners to perceive motifs from previous measures while anticipating future resolutions. Similarly, narrative techniques in literature employ flashbacks, foreshadowing, and interwoven storylines, enabling readers to engage with multiple temporal layers concurrently. Visual arts, from historical murals to modern installations, often juxtapose events from different periods within a single frame, creating experiences in which past, present, and implied future are perceptually accessible at once. These practices demonstrate that humans intuitively construct temporal simultaneity within aesthetic contexts. Scientific observation provides further examples. In astronomy, the study of distant galaxies and supernovae allows researchers to witness events that occurred millions or billions of years ago, effectively observing the past in the present. Predictive models, such as simulations of stellar evolution or orbital mechanics, allow scientists to anticipate future configurations of celestial bodies, integrating foresight with immediate observation. Meteorology and climate modeling combine historical data with current measurements and predictive algorithms to anticipate future weather patterns. In each case, temporal information from past and future sources is operationally present, reinforcing the concept that time is experienced and applied as a continuum rather than a strict sequence. Technological systems extend these capabilities into daily life. Real-time monitoring, predictive analytics, and automated control systems require operators to access historical data while responding to current conditions and anticipating future states. Examples include financial trading, algorithms, industrial process control, and autonomous vehicle navigation. These systems rely on continuous integration of past, present, and anticipated future information, demonstrating the practical application of temporal simultaneity in operational environments. Human perception and technological mediation converge, allowing coordinated activity that engages multiple temporal layers simultaneously. Even ordinary human activities demonstrate this continuity. Driving requires awareness of prior knowledge of the route, attention to current traffic conditions, and anticipation of potential hazards, all integrated into a single ongoing experience. Cooking involves recalling previous recipes, adjusting to present conditions such as temperature and ingredient variations, and anticipating timing for future steps. Conversations require recalling prior context, attending to immediate speech, and predicting responses. Across these experiences, the brain constructs a present that incorporates past and future information continuously, exemplifying the coexisting temporal layers inherent in daily life. Neuroscience continues to reveal the brain's integration of temporal information across past, present, and anticipated future. Studies on prospective memory demonstrate that individuals can plan actions to be executed at future moments while simultaneously attending to ongoing tasks. Functional imaging shows that this planning recruits both the dorsolateral prefrontal cortex and hippocampal regions, linking spatial and temporal encoding with executive function. Similarly, retrospective memory tasks involve reconstructing experiences with attention to sequence, context, and detail, engaging overlapping neural circuits. The simultaneity of these processes indicates that the brain continuously navigates a temporal landscape in which past and future are embedded within present cognition. In physics, experiments with particle decay and quantum superposition further illustrate temporal complexity. Radioactive isotopes decay probabilistically, with measurable half-lives indicating that the exact moment of decay cannot be predicted in advance. Yet the statistical distribution is precisely known. Observing decay events integrates past conditions, the initial isotopic composition, with present measurement and probabilistic anticipation of future behavior. In quantum superposition, particles exist in multiple potential states simultaneously until measurement collapses the wave function, an interaction that links past preparation with present observation and determines the future outcome. These phenomena demonstrate that temporal relationships at the fundamental level are non-linear and interdependent, with past and future states continuously influencing present results. Cultural observances across the globe reinforce the interweaving of temporal layers. Calendrical systems, from the Mayan long count to the Gregorian calendar, track cycles of days, months, and years, embedding historical knowledge while structuring present activity and anticipating future events. Harvest festivals, solstice celebrations, and ritual ceremonies often align with astronomical cycles, connecting human activity to long-term patterns in the natural environment. These observances maintain historical continuity, orient participants in the present, and provide anticipatory guidance, effectively creating a temporal framework in which past, present, and future coexist within communal experience. Long-term scientific projects offer additional insights. Climate monitoring networks record temperature, precipitation, and atmospheric composition over decades, integrating historical measurements with real-time data and predictive modeling. Observatories track celestial events across centuries, combining archived observations with live measurements to study long-term phenomena such as star formation, galactic collisions, and planetary motion. Genomic and ecological studies analyze historical samples alongside current data to project trends in biodiversity, evolution, and population dynamics. In all these cases, the integration of past records, present observation, and future projections allows scientists to operate within a continuous temporal framework in which multiple layers of time are accessed simultaneously for analysis and decision-making. Technological systems likewise capitalize on temporal integration. High-frequency trading relies on millisecond-level historical data, current market information, and algorithmic forecasts to execute transactions. Industrial automation uses sensor networks to monitor ongoing processes, reference historical performance, and adjust operations in anticipation of potential deviations. Virtual reality and simulation platforms create environments in which participants interact with past scenarios and projected outcomes concurrently, blending experiential time across multiple layers. These applications demonstrate that the operational present is constructed through simultaneous engagement with temporal information spanning past, present, and future. Even in individual perception, subtle examples of temporal simultaneity emerge. Skilled musicians anticipate rhythmic and harmonic sequences while drawing on memory of previous measures, integrating performance with prediction. Athletes execute complex movements informed by prior training and in the moment feedback while anticipating the next sequence of events. Readers process narrative structures by recalling previous chapters, interpreting current passages, and anticipating plot developments. Across all these activities, cognitive processes merge multiple temporal dimensions into a coherent, continuous experience in which past and future coexist within the operational present. Astronomical research continues to provide concrete instances of temporal simultaneity. Observations of variable stars, pulsars, and exoplanet transits allow scientists to reconstruct events that occurred years or decades prior, while integrating these findings with predictive models of future behavior. Deep sky surveys compile data over decades, creating cumulative records that link past observations with present analysis and long-term projections. Gravitational wave detection similarly combines historical data, real-time measurement, and modeled predictions to study phenomena such as black hole mergers and neutron star collisions. These practices reveal that temporal information from past and future is continuously incorporated into present scientific understanding, demonstrating operational simultaneity across multiple temporal scales. Human cognition studies further illuminate the simultaneous engagement of past, present, and future. Experiments with event-related potentials show that the brain anticipates upcoming stimuli milliseconds before they occur, preparing sensory and motor systems in advance. At the same time, working memory maintains representations of recent events to inform immediate processing. Tasks such as language comprehension illustrate this integration. Understanding a sentence requires recalling previous words, interpreting the current word, and predicting subsequent words to maintain coherence. These findings demonstrate that temporal processing is an active, continuous operation in which multiple layers of time coexist within the functional present. Cultural continuity reinforces temporal simultaneity across generations. Archival systems, libraries, and museums preserve historical records, artifacts, and knowledge, making past experiences accessible in the present. Rituals and ceremonies maintain social memory, linking current participants with ancestors and prior communal events. Seasonal and agricultural practices encode lessons from previous years while guiding ongoing labor and preparation for future cycles. These systems integrate historical, immediate, and prospective temporal information, allowing human societies to function across extended timescales while maintaining an active engagement with both past and future. Technological mediation extends temporal access and operational capacity. Digital archives enable instant retrieval of decades of historical data, while predictive modeling software provides real-time simulations of potential future scenarios. Control systems in industry, transportation, and finance integrate past performance, current status, and anticipated conditions, allowing operators to act with simultaneous awareness across multiple temporal dimensions. High-speed communication networks further compress temporal separation, transmitting information globally in fractions of a second and allowing decision-making that relies on near-instant integration of past, present, and projected future states. Cosmic observation continues to illustrate the interwoven nature of temporal layers. Light from distant galaxies conveys information about events that occurred billions of years ago. Yet it arrives in the observer's present, providing direct access to deep time phenomena. Observatories track variable stars, supernova, and planetary motion across decades, combining these long-term records with current measurements and predictive models to understand astrophysical processes. Gravitational wave observatories detect events such as black hole collisions, combining historical detection algorithms, real-time measurement, and computational simulations to infer future behavior. Across all these observational domains, temporal information from past and future is actively processed in the present, demonstrating continuity and simultaneity on cosmic scales. Even in daily human experience, temporal layers are continuously integrated. Decision-making often requires simultaneous consideration of past experiences, current circumstances, and projected outcomes. Navigation, whether in physical space or digital interfaces, draws upon memory, sensory input, and predictive modeling. Artistic performance, including music, theater, and dance, requires performers to simultaneously recall prior cues, execute present actions, and anticipate subsequent sequences. In each case, cognition integrates multiple temporal scales to produce a coherent experience, revealing the operational presence of past and future within the present moment. Environmental and ecological monitoring also demonstrates temporal integration. Long-term climate datasets allow scientists to correlate past temperature records with current conditions and predictive models for future scenarios. Satellite observation of deforestation, glacial movement, and oceanic patterns integrates historical trends with real-time data to inform policy and conservation efforts. This continuous engagement with temporal layers enables both scientific understanding and practical decision-making, illustrating how the coexistence of past, present, and future is central to effective observation and action. Technological simulations and virtual environments provide controlled examples of temporal simultaneity. Flight simulators, driving simulators, and immersive virtual reality platforms integrate historical scenario data, real-time environmental feedback, and projected outcomes, enabling participants to navigate complex temporal structures within a single experiential framework. These systems replicate the brain's natural integration of temporal layers, offering a practical demonstration of how past and future can be experienced and acted upon in the present without waiting for sequential progression. Long-term scientific projects provide vivid illustrations of temporal simultaneity. In climate science, ice core sampling allows researchers to study atmospheric composition, temperature, and greenhouse gas concentrations over hundreds of thousands of years. These measurements link past climatic conditions, to present observations and projected future trends, enabling models that integrate multiple temporal scales. Similarly, tree ring analysis records annual growth patterns, revealing historical environmental fluctuations while informing contemporary forest management and future ecological forecasting. These datasets allow scientists to operate across centuries of information in real time, accessing past records, observing current phenomena, and anticipating potential developments simultaneously. Extreme perception experiments further demonstrate the brain's capacity to integrate temporal layers. In high-speed visual tracking tasks, participants monitor multiple moving stimuli, predicting trajectories while recalling prior positions. The neural systems involved, particularly in the parietal cortex, coordinate rapid assessment of past states and anticipated future positions, creating a unified perception that blends temporal dimensions. Experiments with temporal order judgment indicate that even brief millisecond level sequences can be perceived in non-linear order, revealing that subjective experience constructs temporal sequence rather than passively reflecting physical events. Such studies highlight the brain's inherent ability to compress, merge, and reinterpret past and future information within the present perceptual framework. High-speed technological systems exemplify operational temporal simultaneity. Automated trading algorithms execute complex strategies in microseconds, drawing upon historical market data, current pricing information, and predictive models of future trends. Industrial robotics relies on sensors that continuously monitor ongoing processes while referencing prior performance and adjusting in anticipation of potential deviations. Telecommunications networks transmit information globally with near instantaneous feedback, enabling coordination across spatial and temporal distances that would be impossible with conventional human response times. These systems function effectively by integrating temporal layers, mirroring cognitive mechanisms that allow past and future to inform present action continuously. Astronomical and astrophysical research consistently operates across extended temporal frameworks. Space-based observatories such as Hubble or the James Webb Telescope capture photons emitted billions of years ago, providing insight into the early universe while allowing contemporary analysis and modeling of future cosmic events. Observations of variable stars, planetary transits, and galactic collisions combine historical data with real-time measurement and predictive simulation. Gravitational wave detectors, operational over multiple years, track collisions of black holes and neutron stars, integrating prior detection algorithms, ongoing measurement, and model-based projections to interpret signals that unfold across vast temporal scales. These projects demonstrate that scientific investigation inherently involves simultaneous engagement with past, present, and anticipated future phenomena. Daily human activities continue to exemplify temporal integration in practical terms. Skilled performers, such as musicians or athletes, anticipate immediate outcomes while drawing upon accumulated experience, aligning past practice with current execution and future sequences. Language comprehension involves simultaneous recall of prior context, interpretation of ongoing speech, and prediction of forthcoming information. Navigation, whether in driving, aviation, or pedestrian movement, requires continuous assessment of past positional knowledge, current sensory input, and anticipated obstacles or destinations. In each case, Cognition merges temporal layers seamlessly to produce coherent action and perception. Environmental observation provides additional instances of simultaneity. Satellite monitoring of deforestation, glacial retreat, or ocean temperature integrates historical imagery, present measurement, and predictive modeling. Ecological studies of animal migration or population dynamics combine long-term datasets with immediate tracking and projected forecasts. Conservation strategies rely on these integrated temporal perspectives to inform decisions that account for past trends, current conditions, and future projections. Such practices demonstrate that operationally, the past, present, and future are continuously engaged within observational and decision-making frameworks. Further studies in human perception continue to reveal the seamless integration of past, present, and future. In experimental psychology, subjects exposed to rapid sequences of visual or auditory stimuli are asked to report the order of events. Often, participants misreport sequences, perceiving later events as occurring before earlier ones, or blending events into a single impression. These findings indicate that the brain does not passively record temporal information, but actively reconstructs it. Cognitive processing simultaneously references prior experiences and anticipates forthcoming outcomes, producing a perceptual field in which multiple temporal layers are accessible at once. Temporal illusions, such as the flash lag effect, further demonstrate that perception incorporates predictive coding, blending memory and expectation with ongoing sensory input. Historical observation provides additional concrete examples of temporal simultaneity. Astronomers maintain meticulous records of solar and lunar cycles spanning centuries. These data allow contemporary researchers to correlate past astronomical events with present observations and project future alignments. Ancient civilizations, including the Babylonians and Chinese, tracked eclipses and planetary motion with detailed logs, enabling predictions that remain accurate today. By studying these records, modern science accesses historical data directly, interpreting it in light of current understanding and forecasting future events. In this way, knowledge of the past actively informs present observation and future planning, reinforcing the continuity of temporal layers. Environmental monitoring demonstrates continuous engagement with past and future. Glacial surveys compare historical photographs and measurements with current observations to assess changes over decades. Dendrochronology analyzes tree rings to reconstruct historical climate conditions and project future growth trends. Oceanographic studies track currents, temperature, and marine life populations over decades, integrating historical records, real-time measurement, and predictive models. Wildlife biologists studying migration patterns utilize past tracking data alongside current observations and forecasts to understand and anticipate movements. Across these fields, the past and future are operationally present, informing decision-making and enhancing understanding in the immediate moment. Astronomy continues to provide some of the clearest examples of temporal simultaneity. Observations of distant stars, supernovae, and galaxies allow researchers to witness events that occurred millions or billions of years ago, while simultaneously analyzing present signals and modeling future dynamics. Pulsar timing arrays and deep sky surveys integrate decades of observations with real-time measurements and predictive simulations, allowing scientists to track long-term cosmic evolution. Gravitational wave research relies on extensive historical data, ongoing detection, and model-based prediction to interpret phenomena unfolding across vast temporal scales. The combination of past observation, current measurement, and projected understanding illustrates that time in the cosmos is experienced not sequentially, but as an interwoven continuum. Even ordinary human experience reflects temporal integration in subtle ways. Planning daily activities requires drawing upon memory of previous routines, evaluating current conditions, and anticipating upcoming events. Reading involves integrating prior narrative information with immediate comprehension and expectation of plot developments. Listening to music engages memory of preceding melodies, attention to the present sequence, and anticipation of forthcoming motifs. Skilled movement, from typing to sports, relies on the continuous feedback loop of recalling prior actions, executing present motion, and predicting the next step. In all these examples, consciousness operates within a framework where past, present, and future are actively interlaced. Scientific practices, from laboratory experiments to long-term field studies, reinforce this same principle. Geologists studying sedimentary layers integrate prior excavation data, current analysis, and projections of stratigraphic evolution. Meteorologists model weather patterns by combining historical climate data, present measurements, and simulation-based forecasts. Biologists examining population dynamics rely on historical trends, real-time observation, and predicted reproductive cycles. Across disciplines, the operational present is always constructed through the simultaneous engagement with multiple temporal scales, allowing scientists to interpret events with a continuity that unites past, present, and future. In the quiet moments of observation, whether watching a distant star, monitoring a glacier, or following the migration of animals, the coexistence of temporal layers becomes apparent. Past events are directly accessible through measurement and memory, while future possibilities are continuously anticipated through predictive modeling. Present experience serves as the convergence of these temporal streams, creating an uninterrupted perception in which time is not strictly linear, but continuous and overlapping. In this way, the universe, human cognition, and scientific practice all exemplify the operational reality that past, present, and future are continuously interwoven, each influencing and informing the other. Through these observations, a subtle calm emerges. The knowledge that past and future coexist within the present allows for a reflective appreciation of continuity. Scientific records, environmental monitoring, astronomical observations, and human cognition all demonstrate that temporal layers are not isolated but integrated. Awareness of this interconnectedness encourages a quiet attentiveness to the world, a recognition that every observation, measurement, or action is simultaneously informed by what has occurred and what may come. Time, in this sense, is not a strict sequence, but a fluid continuum, patiently observed and navigated, ever present in the ongoing moment.